All right, so 8.2, just a reminder, that was understanding sample space and how to find probability of, say, flipping a coin or rolling a dice, right? So those are generally pretty intuitive. 8.3 is, and depending on how good your year 8 and year 7 probability was back then, some of it may not be as intuitive when you get multiple events, is what they call it. Events means scenarios that you're going to add on. Okay, so here is an example. We usually use, in 8.3, they call it multi-stage because there's multiple ways, but we use what we call a two-way table or a tree diagram, okay? And here's the example. Say I flip a coin, right? And I ask, say, Fanita, if I flip a coin, what's the chances of getting tails? 50-50. So you'd say 50%, right? Then the scenario changes if I said, let's say we flip a coin and roll a dice at the same time. So if I said, what's the chances now? So before you told me, chances of getting tails, you said it was half. But then if I asked you just rolling a dice, if I said, what's the chances of getting a 3? What's the chance of getting a 3? Let's go with Josh. Just rolling a dice, normally.
1 out of 6.
1 out of 6. There's 6 options, and there's only 1 3. But now, if we combine them together, if I flip a coin and roll a dice at the same time, so it comes up simultaneously, then my question is, what's the chances that you get a tails and you get a 3? Okay, so this is where, you know, what? It's not 2 out of 8. it's not 2 out of 12 either.
2 out of 24.
Yeah, and so this is where, how do we then ensure we can calculate it? So this is what we call multi-stage. So you're able to do single stage. Multi-stage is when we add on multiple things, yeah? So here in this case, you told me you knew flipping a coin had either heads or tails. You also knew that rolling a dice was 1, 2, 3, 4, 5, or 6. Now, in these scenarios, you can use either a two-way table or tree diagrams to visualize what's happening. To me, in this scenario specifically, two-way table is probably better, and I'll show you what it looks like. A two-way table, you literally list 2 options. So rolling a dice is up here, 1, 2, 3, 4, 5, 6. Flipping a coin is heads or tails down there. So together, the chances, the possibilities that you can get is you might get heads and then a 1. Okay, so let's have a look. So if we have a look here, how many total options can I possibly get? 12. So I've got H1, H2, H3, H4. I could get heads and then 5, heads and then a 6. Another option is I could get tails and a 1, tails 2, tails 3, tails 4, tails 5, tails 6. So in total, it's out of 12, right? So it's easy to see now that it's actually 12 options, but how many of those is a tail and a 3? How many is a tail and a 3? So how many can you see there is a tail and a 3? There's only one where you can get a tail and get a 3. So there's only one option that you're looking for out of the 12 possible options. You see that? So initially this one was easier because in a single stage, you can see the total options, heads or tails. Rolling a dice, you can see it's 1, 2, 3, 4, 5, 6. The problem is when you add 2 things together, you then got to think about what are all the possibilities you can get. You can get heads with a 1, heads 2, heads 3, heads 4, heads 5, 6. You list out. The two-way table works because you get 2 events. So here, what are the pros of using a two-way table? It does really well to keep information condensed, so it's easy to see. Yeah. Problem? You can only do it for 2. Because if I said roll a dice, do a spinner, and flip a coin, then two-way table won't work. Because it only works for 2 dimensions. It doesn't do 3. So, tree diagrams, when you get 3 options or more, then you want to use a tree diagram. So this is what a tree diagram would look like. Branch 1, so you get heads or tails for flipping a coin. But after you flip a coin, you could get 1, 2, 3, 4, 5. Oh, I'm missing 6 as well. And then same thing with tails. You can get 1, 2, 3, 4, 5, or 6. And that way you can see what's your total options. You can count from here. That's now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. That's one way of doing it. Now, what's the con of tree diagrams? Looks very messy. And a lot of students find it tricky to draw to begin with. Whereas two-way tables, a bit more intuitive. Easier to see, condensed, but there's a con to it. It only works for 2 outcomes or 2 events. When you have more than 2 events, tree diagrams are better, but it can get messy. Okay, so both of them still get a total out of 12. So if you count them, you get 12 options. And out of all of them, there was only 1 tail and a 3. So it's 1 option out of the 12 options that you've got there. This one I was missing the 5, so H6. And this one I was missing T5. So that's why it's 11 and 12 there. Okay. Oh, I'm missing T4. Sorry. Whoops. T4. There we go. Cool. So that's the difference between the two. Now let's do an example just to get you guys practicing. It's either two-way tables or tree diagrams. Okay. Here's an example. Look at example 1. You got 2 spinners. So it's not just 1 spinner now. So one spinner has 1, 2, 3, 4, 5 as a number. And the other one also has 1, 2, 3, 4, 5. Are there 25 options? Yes, you're right. Because it's 5 by 5. Very good. So since there are only 2 events, because you only got 2 spinners to work with, a two-way table is better. So when they say calculate the probability of getting at least 1, now be careful with that question there. We want at least. What does at least mean? Minimum. So you can get a 2, you can get a 3, you can get a 4, you can get a 5. Now if you look at this list here, we can say you can get 1, 1, 1, 2s, 1 and a 3, 1 and a 4, 1 and a 5. This is 2 and a 1, 2 and a 2, 2 and a 3, 2 and a 4, 2 and a 5. Whoops. 3 and a 1, 4 and a 1, 5 and a 1. Actually, you get the whole point, right? We can fill it all out. But what do they mean by calculated probability of spinning at least 1, 1? So out of those options there, how many is at least 1, 1? Not all of them. So I haven't filled out the table here, but if you think about it, this one doesn't have any 1s. This one you get a 3 and a 3. This one you can get a 3 and a 4. 3 and a 5. This is 4 and a 2. Doesn't have any 1s. 4 and 3 doesn't have any 1s. 4 and 4 doesn't have any 1s. 4 and 5 doesn't have any 1s. So how many actually has at least 1, 1? Because we want at least 1, 1. 9, let's count. Here we go. We've got 5 here that has at least 1s there. All of these definitely have 1s here. Okay. And if you count that, that's 5 plus 4. That gives you 9. Very good. Okay. So again, listing the two-way table allows you to see it. But if you didn't do it with some diagram, it's harder to visualize. Right. So the purpose of using two ways versus tree diagrams is to help you calculate better. Here we go. 5, 2, 5, 3, 5, 4. 5, 5, so you are correct. What's the probability of at least, so minimum, 1 of these 1s? The answer is out of 25, there are 9 of them that you can get. Okay, so it's not so much that it's the probability that you're having troubles with, it's the finding out the total. So knowing the total and then calculating from the list, which ones do you want? So the problems can change and make it a bit difficult. So for example, the next page, flip over. I'm not going to guide you on this one yet. I'm going to get you, maybe I'll give you 4 minutes to try to attempt A and B. Just get a vibe of how would you calculate this if I wasn't here and it was on the exam. How would you work out the chances? Okay, so I'm going to flip over the page. You got a uniform committee now. At Viewbank College is deciding on a new color combination for the school uniform. So for pants, you can choose gray or black. For a shirt, you can choose white, navy, or black. For a jumper, you can choose navy or black. Okay. Now, A and B, A tells you to try to visualize it, because if you try to do it in your head, it's going to be hard. Use a tree diagram to show all the possible combinations that you can get. Okay, so for pants, you need to choose a pants, you need to choose a shirt, and you need to choose a jumper. What are the total possibilities that you need? Because you need to know the total. Then B is calculate the probability that uniform will consist of only one color. Have a go. You got 4 minutes. How would you tackle that problem? Do it in your head, but using a diagram will help you. Pause the video. That's beast.
My back, like, it was definitely just shoulders on the
Did you do what they do in the videos where you go?
Yeah, I did it.
Here we go. Tree diagram. This is what you should have got. Option 1, pants. You can get either grey or black. Grey or black. That's pants. Oops. Then you can do shirts. You can get white, navy, or black. So white, navy, or black. White, navy, or black. And your last one, after you pick a shirt, you then pick a jumper. So your third event was pick a jumper, and you can get either navy or black, 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 navy or black.
What's the JB? Oh, is that girls' boys?
No, that's grey black. Grey or black. So I just used the letters of each one. So for pants, for the first event, you can either get grey or black. Once you pick a colour for the pants, pick a colour for the shirt, you can either get white, navy, or black. Once you pick a colour for a shirt, then you can pick jumper, you get navy or black. Now, if you want to now know what's the total number of options there, you can count them all. So the final one tells you the number of counts. So you could have got grey pants, white shirt, and then a navy jumper. That's one option. So how many options in total? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now the quicker way, instead of doing this counting method, if you guys want to know a shortcut to it, just times them. So this one was 2 options for the first one, times 3 options for the second one, times by 2 options for the third one. So 2 times 3 is 6, 6 times 2 is 12. So rather than counting the way I just did, it was actually quicker if you just multiplied the number of options. So it would have been 2 times 3 times 2, and you know the totals out of 12. Okay, so that's a quick way of doing it, but if you don't remember it, the diagram, if you draw it out correctly, you would have got 12 options. Okay, so it should be out of 12. All right, now let's answer the first question. B. Calculate the probability that uniform will consist of only one color. So if it consists of only one color, that means in one row, I should only see the same letters across all of them. Now, which one has the only same colors or same colors across all of them? I can see black over here, black pants, black shirt, black jumper. That's one option. Any other ones that is tripling up? No, I think that's it. I think black was the only one that was most consistent in all 3. So what's your probability? Probability is 1 on 12. Out of 12 options, there was only one where you can get all the same color. Okay? So all same color, which means black pants, black shirt, black jumper. Had to be 1 out of 12. Okay, so drawing the table is probably one of the trickiest skills to then figure out. But once you're able to draw it, then you can figure out the total number of options. Okay, let's see. Now that I've got the diagram there for you, can you figure out C? Calculate the probability that a navy jumper will be part of the uniform. Okay, jumper. So jumper's the last column. How many of those have a navy jumper? Okay, you got 1, 2, 3, 4, 5, and 6. So it would be then 6 out of, which is half. So half of them. Okay, so probability with a navy jumper. Yep. Jumper is equal to 6 out of 12. Half of them will have a navy jumper. And then finally, D, calculate the probability uniform will be grey pants. So you want a grey pants, a white shirt, and a black jumper. So you want the probability of grey pants, white shirt, was it? White shirt, black jumper. White shirt. And I think you're right. Grey shirt, which is over here. Grey pants, white shirt. Yeah, and there's only one. Yeah, there's only one option for that to work out. So therefore, it's 1 out of 12. Okay, so the tree diagram will be useful if you draw it correctly. If you draw it wrong, then everything else is wrong. But that's a small part of the exam. It is something you need to know, but it won't be a big part in the exam. Okay, so most times it's a bit more logical, looking around. But in your SAC, I will be putting in some probability questions in there. So you do need to know some of these logical tools to help you visualize it. Okay. But that's it for today. So 8.3 to me is the most calculating of them all. The rest was pretty straightforward. 8.2 was intuitive. And then 8.4 is just going to be Excel simulation. So knowing interpretation long term. Okay.
Excel stuff won't be on there. Is that correct?
No, they will be. That's why it's been moved.
Jesus, then how do we do it on Excel?
No. Oh, so that's what you meant. No, so you won't be doing simulation, but it'll be questions like, once you work out the probability, I may ask you, like, why is the experimental probability different to the theoretical? Then I might say, in the long term, what does this mean for, say, if it was a gambling scenario, then what does it mean in the long term? So that's 8.4. So that scenario would mean that you have to know, in the long term, the student is, if they're gambling, they may be losing, say, 5 cents for every game. So in the long term, how much money would they roughly lose? That's simulation.
What's the point of gambling? That's 5 cents.
No, 5 cents for every game. So it depends on how many games you play in each hour. Then, on average, how much would you lose in the long term?